Hello everyone, my name is Suraj and I'm a graduate student at Oklahoma State University. Today I'll be presenting our work on hybrid analysis and modeling for next generation of digital twins. And this work was done in collaboration with Shadi Ahmed and Omer San at Oklahoma State University and Adil Rashid at Norwegian University of Science and Technology. So what is digital twin? A digital twin can be defined as a virtual replica of physical systems enabled through data collected from sensors and numerical simulation, and that will allow us to solve problems such as optimal control, optimization. This in turn will lead to the improved decision making. One of the major challenges with digital twin is the type of the modeling approach that you'll be using to approximate the physical system. So the model should be such that it will bring the physical realism to the digital twin. So basically, the model should be computationally efficient, trustworthy, accurate, and generalizable. Another feature the modeling approach should have is that it should allow the seamless integration of multi-physics, multi-scale, and multi-fidelity problems. So the state of the art methodologies in digital twins is either based on physics or based on the data. Both of these approaches has got certain advantages and certain limitations. For example, the physics-based modeling is based on solid foundation and has good generalization capability. On the other hand, data-driven modeling is considered to be a black box approach and also has poor generalization on unseen problems. So in last few years, there is a new term that is emerging called as hybrid analysis and modeling. In hybrid analysis and modeling, we try to combine interpretability, robust foundation, and understanding of physics-based approaches with accuracy, efficiency, and automatic pattern identification of data-driven methods. The model from HAM will be such that it will give the less uncertain results in a computationally much less time. In this work, we propose two different approaches under HAM paradigm. The first approach is called as physics-guided machine learning or PGML. So the main motivation behind PGML is to make data-driven model more certain. We apply this framework to the task of real-time aerodynamic force prediction around airfoil. So we can try to predict the lift coefficient and the flow around airfoil using CFD simulation. But these CFD simulations are computationally very expensive. Therefore, we want something which will give much faster results. And for that, we build the neural network-based surrogate model. So we use the shape of the airfoil as input features. We also know that the Reynolds number and angle of attack has got a very significant effect on the lift coefficient of airfoil. Therefore, instead of using these features as an input features, we combine them with the latent features that are being learned at certain hidden layer. We also use the prediction from simplified methods like panel method. And basically what it does is that it will make sure that the prediction from neural network will lie on the physically realizable manifold. And this in turn will produce the results that are more generalizable to unseen condition. The second framework that we propose is called as interface learning. And we apply this to the problem called as Boussinesq equation. So in Boussinesq equation, we solve the temperature equation and the vorticity equation. Therefore, instead of using the full order model for both equation, we use the physics-based form for the temperature equation, and we use the data-driven reduced order model for the vorticity equation. And both these equations are connected via stream function. So there is a two-way conflict between temperature and vorticity equation. We propose three different variations of interface learning framework. The first one is called as a direct prolongation interface, in which case the flow field that is being reconstructed from the ROM is directly matched with the form results. The second method is called as a correction followed by the prolongation interface. And in this approach, we correct the model coefficient in the reduced subspace. And these corrected model coefficients are in turn used to reconstruct the flow field, and that flow field is used as a boundary condition at the interface. The third approach is called as the uplifted prolongation interface, in which in addition to correcting the model coefficients, we also include the more model coefficients, and that in turn will solve the projection error. And basically we use all these coefficients to reconstruct the flow field, and that will be used at the interface boundary condition. So let us look at the results with these two frameworks. The first result over here basically shows the variation of lift coefficient with different angle of attack for two different airfoil shapes. We highlight here that we do not have the NACA 230 airfoil shape in the training data set. Also the 23024, that is a 24% of the airfoil is like the maximum thickness that has not been used in the training data set. And if you see the results, you can see the results of the prediction from the PGML framework has much smaller uncertainty bound as compared to the ML method. And this is especially significant in the angle of attack between -10 to 12, and that is usually the operating range of the airphone. The results for the interface learning is shown over here. And if you see, the CPI and UPI approaches are able to accurately predict the flow features, especially between the x equal to 7 to 8 and between 0 to 1. Uh, to conclude, we propose a novel deep learning architecture, and that will enable us to inject the features from simplified theory. And this will give us the model which are more certain. And we observe that there is a 75% reduction in uncertainty for the aerodynamic force prediction task. The second framework, that is the interface learning technique, couples the data-driven ROM and full-order model, and that can give us computational speed up to 10x improvement over the full-order model. And with this, I would like to end my presentation, and thank you all.